Agrenush Korja, welcome back. My name is Paul Cunningham. Welcome back to the third day of IST-Africa 2022. We're now on the afternoon of the 18th of May, and we're looking at the next generation computing session. This session is going to share experiences from South Africa, from Botswana and Mauritius. And we're starting with a presentation on preliminary experiments on the performance of machine learning models.
Welcome to our paper presentation. This paper was authored by Misheck, Banda, that's me, Enes Kechangasim, and Enes Mkandla. We are all from the University of South Africa. I will be presenting this paper entitled The Preliminary Experiments on the Performance of Machine Learning Models. Before I get into the main discussion of the paper, I would like to thank you, IST-Africa Institute, for publishing and accepting our paper to be part of the IST-Africa 2022 conference proceedings, and for this opportunity to present it. I also want to briefly share what to expect during this presentation. The paper has several slides, starting with the introduction, which briefly talks about the AI-related technologies and what we are trying to achieve, followed by the discussion on the ML models selected. Then I'll discuss the simulation environment we used, the experiments we did, the evaluation of ML models, and the dataset used. After that, I will discuss the process followed during the comparison experiments, the results, and the interpretation of the performance. The last two slides will address the business benefits and the summary conclusion. So to start, I would like to give you a brief introduction in the next slide. Artificial intelligence has become part of our daily lives since its inception in the last half of the 20th century. AI's focus was to be super fast when responding to the given tasks. However, the first quarter of the 21st century, also known as the Fourth Industrial Revolution, has its core focus on developing AI technologies that have human-like capabilities. At the core of this quarter of the century is building or developing computer learning capabilities, also known as machine learning, which implies that computer systems must have the learning capabilities of human beings. This paper considers a range of machine learning models in the literature and empirically evaluates their performance given a data set. These experiments to predict the likelihood of passengers surviving the Titanic disaster are the preliminary, because this research paper forms part of a series of experiments to identify suitable ML models. Our preliminary experiments only used historical datasets to set the foundation for the series of papers to evaluate the ML model's performance. Now let's talk about the models we considered. Three ML models were selected for this first series of model evaluation experiment using a supervised learning environment. The first is the logistic regression model, which is mostly used for categorical response data in various applications and studies, and have the benefit of combining qualitative and quantitative predictions. The second is decision tree, which are nonlinear classifiers that use a series of decisions along the path of nodes to reach the desired outcome. For this reason, a decision tree fits many purposes. It is more concise ML model and has the advantage that it can be visualized more easily. Last but not least, the random forest model is ideal for classification and regression problems. It's primarily based on trees like the decision trees. However, random forest uses a technique that reduces the possibility of having a variance resulting from a slight change in one of the higher nodes. The authors selected these models because they are among the most used ML models and are good candidates for continuous improvement to meet the ever-growing data management requirement. It must be noted that the paper did not predefine the problem definition and then collect the needed data, but we looked at the available datasets from the data sources and tried to understand what information could be extracted. So to achieve this, let me talk about the simulation environment we used. We chose the Anaconda distribution of Python, an open source software that comes with the most used data science language, libraries, and packages. This paper used the following language, development, environment, and libraries. Python version 3.7, which is the most recommended language for data science and machine learning. We used the Jupyter Notebook environment version 6.0.3, which is a web-based integrated development environment that supports interactive data science and scientific computing. We also used NumPy library, which is a core package for scientific computing in Python. We used Pandas, a high-performance data analysis library in Python with tabular data structures, data analysis, and data modeling tools. Matplotlib library, we used it as a data plotting and visualization tool to generate simple and complex two-dimension plots. We also use Seaborn library, which is a statistical data visualization library based on Matplotlib. And last but not least, we use Scikit-learn library, which is an integrated, powerful, and versatile ML library which played a pivotal role in fitting, training, and performing predictions. Now let's talk about the evaluation metrics we used. The performance of the models was measured by considering some classification error metrics such as the recall metric, which measured the model's effectiveness in finding the correct output and denotes its sensitivity in classifying the features or the variables involved. The precision matrix was used, which defined the ratio of correct classification to the total number of training inputs. And the F1 score combined the recall and precision matrix, which was the computed average score, also known as the harmonic mean of the relevant two values. In addition to the above mentioned metrics, a confusion matrix was used to demonstrate further the number of correctly classified true positive, true negative, false positive, and false negative. Now it's time to talk about the Titanic dataset we used in the next slide. We acquired the sample datasets for the model evaluation from Cargo, which is a reputable source for machine learning datasets. The Titanic datasets were used consisted of the passenger data of the most infamous shipwrecks in history. The incident happened on the 15th of April 1912, where 1,502 passengers died out of the 2,224 passengers. The dataset had 891 entries with 12 columns consisting of numerical and non-numerical values. This dataset was suitable for this experiment because it was categorical in nature. It's now time to walk through the process of the model evaluation in the next slide. We started with importing all the initial necessary libraries, that is pandas, numpy, matplotlib.pyplot, seaborn, and matplotlib inline, which ensured the graphs displayed within the window of the notebook. But please note that not all the codes are included in this paper. Only a few screenshots were utilized for reference. Step 1 was dataset sourcing. The training and testing datasets were loaded once using the pandas read_CSV function. Step 2 was dataset cleansing and preparation. As expected, the dataset had all sorts of issues such as missing values, outliers, unclear headers, inconsistent formatting, categorical data that needed to be converted to numerical data. Therefore, this ML model evaluation process utilized the NumPy and Pandas libraries, power and functions to cleanse the data and transform it into usable data set, as shown in the two tables below. For example, one of the data converted was in the sex column, which became the male column with values 1 representing males and 0 for females. Once the data cleansing and preparation was done, we exported and visualized the data in the next step. In step 3, data exploration and visualization. The findings were presented in the graphical and/or statistical presentation. A few selected functions from the pandas, matplotlib, and seaborn libraries were used to display the patterns, trends, connections, and relationships. In step 4, training the model. In this step, the models were trained using the feed function after evoking the train_test_split function, which divided the sample dataset into 4 portions. 2 for training, that is x_train and y_train, and the other 2 for testing, that is x_test and y_test. The training dataset was the largest portion to ensure the ML models had enough data during the training. The testing dataset was the smaller portion used to predict and test the model's performance and accuracy. Trained predict function and the x_test and y_test variables played a key role during the testing process. So the predict functions data the train models performance. They evaluating the model. The required metrics for the evaluation were imported from the scikit-learn library displayed below. The output information displayed below played a key role in interpreting the model's performance. It must be noted that the interpretation was mainly on how the models performed in terms of the weighted average score, F1 score, a true positive result or a negative result, and the performance speed in milliseconds. The logistic regression model had the highest prediction scores across all metrics scores. That is the weighted average of 80% and the F1 score of 83% for likely not to survive, and 75% for likely to survive, and yielded the highest true positive value of 107 for likely to survive. The magic command was used to measure the time the datasets took to load, train, and predict. It took 9.01 milliseconds to load the two datasets, which was quick. The logistic regressions model took 72.28 milliseconds longer than the decision tree model to be trained. When measuring the prediction speed, the difference between the logistic regression and decision tree model was smaller, that is 0.97 milliseconds. It took the random forest model 45.03 milliseconds longer to train. Now that the results and model performance interpretation has been discussed, it's now time to talk about the business benefits. The ML models applied in this research paper's experiment can use multiple variables. For example, all the variables of the final passengers trained datasets can be used to determine the likelihood of a passenger surviving. When a decision tree model is used, it will check other variables rather than just focusing on one variable with two defined outcomes like the case for the above experimented model prediction. For example, if a passenger class variable were needed to be checked, this model would have used another node to check and predict the class used. Like the decision tree, a random forest adds another technique that prevents the errors on a higher node from spreading to the rest of the nodes. Real-time prediction can be achieved considering the speed these models could predict. Prediction accuracy can also be achieved given the high scores that predicted the passengers likely to survive. To conclude, this paper considered the logistic regression, decision tree, and random forest ML models, and they were subjected to an experiment under the same conditions using the same dataset. The ML models used were confirmed to be the right ones for predicting classification problems using categorical datasets. The purpose of the experiment was to demonstrate that the desired results can be achieved using the appropriate ML models that suit the dataset to be utilized for a given business problem. This was confirmed through the results of the predicted outcomes of these experiments. The logistic regressions model's prediction of the passenger's likelihood of survival was the most suitable for the dataset used, and it obtained the highest prediction scores across all metrics. The dataset used were historical, and for future papers, the utilization of a combination of near real-time and historical data will be considered to enhance the understanding of the performance of the evaluation. The ML models used were independent of each other and were not used in conjunction. It is recommended for future research to compare the performance of the models and explore how well a combination of models can be used to resolve a given business problem. This way, the models will complement each other where weaknesses are identified. Welcome any questions or comments if the time will allow us. Thank you.
Thanks, Misheck. So we have a question from Avashna.
Thank you. Let me just check the question. Okay, so any fine tuning, not necessarily. We just use the standard testing. The models were just tested using their standard configuration. And this tuning, obviously, is part of the ongoing experiments that we'll be doing to improve and see how the performance can go up. The second question, single test was used. It's only that you can't elaborate more, but yes, basically the test that was done was basically we did the first run of the test using the same data set, and then the results were presented. But when we did the previous tests, we found that the performance wasn't really changing, obviously because of the fine tuning which wasn't done. Hence, the future experiments will basically consider doing that as well. Did you try cross-validation? Cross-validation was not necessary for these data sets because of the learning curve for this type of models is basically, it's usually, there's not much you can achieve, you know. When you do a cross-validation, yeah, basically there's not much you can do after you start doing the validation because of the limitation of the models themselves.
Avashna, do you want to unmute yourself and clarify any of those issues?
Thank you for your talk. So I was just curious about the testing. So you've just basically separated the data set into a single training and testing data, right? So
yes,
what I meant by cross-validation is basically you do several iterations of this where you divide your training set and your training set and your test set into different portions of the same data set, just to see how your test results differ from one another, because it basically improves the generalization of the model if you do this. So that I was just curious whether you tried that. Oh,
okay, understood. Thanks for that. No, basically, once we had set up just the initial portion of, you know, the division of the training set and the other test set, we just used that part of the data itself. So in future, for us to understand more in terms of obviously, or even trying to improve the performance of the model, we'll obviously explore those options as well.
All right, thank you very much. Thanks, Avashna. Does anybody else have any other questions or comments for Misheck? If not, thank you very much. And we'll move on to our next presentation, which is focused on multi-MelGAN voice conversion for the creation of under-resourced child speech synthesis.
Good afternoon. My name is Avashna Govender, and I am a senior researcher and developer at the CSIR in South Africa. In my presentation today, I will be going through my paper on multi-MelGAN voice conversion for the creation of under-resourced child speech synthesis. This work falls under artificial intelligence and more specifically human language technologies such as text-to-speech synthesis. First of all, I would like to start off by explaining what voice conversion is. Voice conversion is the process of modifying a speech signal that has been uttered by a source speaker, like speaker A, to sound as if it was uttered by a target speaker, like speaker B, whilst maintaining the linguistic information, which in this example is hello. So why is voice conversion important to us? Well, in the world of text-to-speech synthesis, we want the output voice to sound identical to some specific speaker. In addition to this, we want to be able to create a text-to-speech system that can cater for a variety of speaking styles, accents, and voice characteristics, depending on the context in which the system is used in. For example, in a language learning application that is targeted at children, we would ideally want a voice that sounds like a child. However, there are currently not many child text-to-speech voices available, especially in our local South African languages. So therefore, the main objective of this work is to successfully build child voices. The major challenge that we face in building such voices is that we are heavily constrained in terms of the data. Collecting child data is extremely difficult, time-consuming, and expensive. And therefore, we are required to use voice conversion methods that enable us to convert from adult speech, which is considered to be highly resourced, to child speech, which is under-resourced, and therefore means having to work with a very limited amount of target data. Also, typical voice conversion techniques that produce high-quality output use parallel data, which means that both the source and the target speaker are exactly the same. However, in the case of using adult and child speech, this is extremely difficult to obtain, and therefore we require a method that is capable of using non-parallel data. Lastly, in terms of voice conversion methods, what is typically used is a single model method that converts from one speaker to another. However, in this work, we attempt to build a many-to-many voice conversion system that is capable of converting several speakers simultaneously. In this work, we adopted the MelGAN voice conversion architecture, which is derived from the GAN architecture, which stands for Generative Adversarial Networks, and is commonly applied in the world of computer vision for the generation of images. So in this figure, I present a classic GAN architecture, which comprises of your two main components, namely your generator and your discriminator. Now, the role of your generator is to learn a mapping from your random input noise to the target image that you want to generate. And the role of the discriminator is to learn to discriminate between your real and your fake images. So in this architecture, both these models work together. For example, we will start off by training the discriminator to a certain point where it becomes fairly good at telling the difference between your real and your fake images. Your real images come from your training data, which is what we want to generate, and your fake images is the output from the generator, which at the beginning will produce really bad outputs because the generator hasn't been fully trained yet. Now, if the discriminator finds it easy to tell the difference between the two, this means that the generator is doing a really bad job. And if the discriminator battles, then that means that the generator is getting really good at producing realistic images, which is what we want. Now, this is measured using some kind of a loss function, which I'm not going to get into right now because we don't want to get lost in the maths. But the important thing to note is that there is some kind of loss, which is then applied in order to fine-tune the training of the generator. And at some point, the generator will start to converge. Now, applying this to speech, Generally, we think of speech as an audio signal, but speech can be represented as a two-dimensional image called a spectrogram. And with further digital signal processing, it is typically represented as what we call a MEL spectrogram, which looks like the images that are shown in the slide. And this is why the GAN that is used in this work is called a MelGAN. The MelGAN architecture is shown on this slide, which, as you can see, is slightly different from the generic GAN architecture that I showed to you on the previous slide. Now, the main difference to observe here is that it comprises of what we call a Siamese network, which is denoted by the S blocks. Now, the only thing that is important to note here is that the Siamese network is used for preserving the linguistic information from the source to the target signal. In other words, when we provide some input signal, for example, the speaker says hello, we want the output to sound like the target speaker, but it needs to still say the same words. The models trained in this work used 3 hours of speech data from an Afrikaans adult speaker, Antoine, and 3 hours of speech from an Afrikaans adult female speaker, Nadia. The target speakers are Johan, who is an Afrikaans male child of age 12, and we used approximately 1 hour of data from him, and Alsha, who is a female Afrikaans child, also around the age of 12, and we used approximately 24 minutes of speech data from her. I first trained 2 baseline voices, which used a one-to-one voice conversion method that converted from a single adult speaker to a single child speaker. I will now play you some samples so that you can hear what the output of these voices sound like. So first we're going to start with the human speech of both the male adult and the female adult.
Die gevoel was asemrowend lekker.
Die gevoel was asemrowend lekker.
And now I will play you the generated speech using the one-to-one model, which then produces your child voice, Johan and Alsha.
Die gevoel was asemrowend lekker.
Die gevoel was asemrowend lekker.
Building a one-to-one model is considered to be impractical because for each new voice that we want to be able to create, we would need to train a separate new model, which can be expensive and time-consuming. And therefore, we modified this model to become a many-to-many voice conversion model or a many-to-one voice conversion model, which we then evaluated against the baselines. So I'm now going to play you the samples of the generated speech since you've already heard the human speech of the adult speakers. So here in the first model, we have both the adult speakers, which would then converted to Johan.
Die gevoel was asemrowend lekker.
And from these results that we will see in a few slides, we found that the multiple many-to-many voice model worked better than this model, and that is why we did not bother to build this model for the female voice. Okay, so for the many-to-many, here is Antoine converted to Johan.
Die gevoel was asemrowend lekker.
And then we have Nadia converted to Alsha.
Die gevoel was asemrowend lekker.
The voices were all evaluated by listeners through a web browser using a Mushra test as shown on the slide. So here the listener was expected to listen to an audio sample and rate it out of 100 based on how natural the sample sounded or how close it sounded to the respective reference human speech which was supplied. So in a Mushra setting, you have all the different conditions displayed together so that the listener is able to make a choice by listening to all of the samples and rating them accordingly. So here are the results for the male child evaluation, which is illustrated in these box plots. So we can clearly see that human speech is significantly better than the generated speech, which is expected, And we then also see that the baseline voices appear to perform better in naturalness than the proposed models, but in terms of similarity, both the proposed and the baseline voices are similar. So here are the results for the female child evaluation, and like in the male evaluation, we can clearly see that the human speech is significantly better than our generated speech, again, as we expect. And we also see that in this case, the proposed models perform better than the baseline models in both naturalness and similarity. Based on these findings, we have demonstrated that it is possible to create child speech using voice conversion methods that convert from a source adult speaker to a child target speaker using a limited amount of speech data that is non-parallel and uses several speakers that are trained within a single model. It is important to note that there appears to be a gain when the amount of target data is less than 30 minutes, which we observed in terms of our female child evaluation. And our intuition around this is that by building a model with several speakers, the model is able to compensate for the speakers that have significantly less data. However, the overall quality was rated at less than 50% in terms of its naturalness, which is not sufficient enough to be used in real-world applications. And therefore, our future work will entail using this many-to-many model as a tool for data augmentation to generate more speech data that can be used as training data in order to develop more personalized and customized voices. Given that current state-of-the-art models are extremely data hungry, and we are working in the environment of very under-resourced languages, using a voice conversion model like this in order to produce more training data will enable us to increase our data sets so that we then will have sufficient amount of data to use state-of-the-art techniques. Thank you for your time and your patience in listening to my presentation, and I look forward to answering your questions. Goodbye.
Thanks, Avashna. That was interesting. Can you briefly discuss first the challenges that resulted in the smaller data set from the male and female children?
Okay, so first of all, I want to say that collecting child data is in itself it's a huge challenge. Just to give some background, when I was doing my master's, this is when I started building child voices before deep neural networks had taken over. And at that stage, I tried to collect data from 2 children, ages 7 and 8. And when I collected that data, it took me 8 hours to collect 8 minutes of usable speech data, which 8 minutes of data is close to nothing, especially when you're trying to train nowadays a deep neural network, which is extremely data hungry. So that
just before you go on, can you clarify briefly, was that because you needed them to say certain consonants or vowels in certain combinations, or was it lack of concentration, or was it background noise, or what was the issue?
So it actually was both. So the first issue was that the children basically have to sit in front of a computer and read text off a screen or off a page, and we have to record them. And the reason why it's difficult is because when you're developing text-to-speech systems, the voice needs to be relatively neutral. You can't have the child reading with expression or emphasizing certain words, which is really counterproductive, because in school, this is how they are taught to read, and now sitting them down and asking them to read sentences in the complete opposite way that they're used to reading. So that was one struggle. And the second struggle was definitely concentration. Children just don't have the attention span to sit and read out sentences for long periods of time. And that's why it took so many hours. And in between, I would need to play with them and take them outside and play some sports with them in between doing the recording. So it can take a really, really long time to collect data. And
No,
that is
I
why,
think, yeah, I think you need to be extremely patient and to like the children, not just children in general, but the specific children you're working with. You need to like them to be able to do that. But it's also, I think, quite interesting for people to realize that while you might think intuitively that having emotional expression when you're speaking would be useful in terms of data training, because you're trying to use the subcomponents of the speech in a variety of different contexts. That's the reason, presumably, why you need it to be neutral rather than expressive. Is that a correct interpretation?
yeah. So like I said, at that stage, it was before deep neural networks had taken off, and we were using hidden Markov models at that stage. And so
Gotcha.
you had to kind of train the models with a neutral voice. But now with the introduction of deep neural networks, we are moving away from this, read speech and more to more casual, spontaneous speech. So perhaps it could be easier, but then it just means that we have to work harder at making our models more robust to this kind of data.
Yeah, so I daren't guess how many hours was involved in getting 33 minutes of the female child's voice. Can you also, maybe before I open the floor to anybody else, could you talk to us about potential ethical considerations? Because obviously you're interacting with real live people. So what potential ethical considerations do you perceive are associated, first of all, with voice conversion models, and then obviously with engaging with children to access their speech samples? Thanks.
Yeah, so definitely ethics is important here because we are working with minors. So before working with projects like this, it is important for the CSIR. We have an ethics board that we have to submit an ethical application that will state that we're working with minors and that they're obviously not harmed. We have to go through all the protocols in terms of getting consent from the parents. And all of those protocols are in place before we are even allowed to start, working with kids. The one thing that we're moving now towards in our research group, because it's so difficult working, getting ethics, because it kind of holds you back, because it takes a long time to get ethical clearance. It can take up to 3 to 6 months to get the ethical clearance for minors. We're moving more towards casting agencies that then find, children actors who are already kind of trained in being able to speak sentences, and this will make our life a bit easier. So hopefully moving forward, we're going to be able to collect a lot more data than we did previously. In terms of, I would say, from the aspect of just ethics in general of collecting data from children, I don't think that it's dangerous because of the fact that children's voices change as they grow older. So obviously what we sound like as a child and what we sound like as an adult, our voices change over time. And so we feel that in building these child voices, it's not going to put the child in any harm, because we will ensure that in our models, if we are using these multiple models that I described in this paper, we're using several speakers simultaneously. So it makes it very difficult to actually trace back to the original speakers. And so their identities are kept anonymous.
Yeah, no, I appreciate that the privacy issues are addressed. I was more looking at it from the social engineering risks of, you currently have, unfortunately, adults in certain contexts pretending not to be adults when they're engaging with minors. And if we get to a stage where in the wild, it's possible to do quasi real-time conversion of voice from an adult voice to a younger voice, I'm concerned with some of those ethical considerations, which I appreciate are outside the scope of your current work.
Yeah. I mean, I guess there's dangers just in general of being able to produce voices in general, because people can use it for malicious purposes. But yeah, that's obviously outside of the scope of this work, and we see the bigger picture of the importance of why we want to build child voices, because in the bigger picture of things, especially in the educational sector, we think that this is, a valuable thing to have.
Yeah, no, I agree. I just would caution that it might be worth considering how this type of speech technology has to be assessed in the context of video deep fakes. You know, so in one sense, a video deep fake, the human eye is so sensitive it can pick up a lot of fakes. But as the technology gets better and better, that becomes more of a risk. And I think the same could be
Yes.
true for voice as well.
Yes.
So does anybody else have any questions or comments for Avashna? That was very interesting, Avashna. Thank you very much indeed. So the
And
next, thank you. And so the next presentation is focused on word-based Bantu language identification using Naïve base.
Hello everyone, my name is Boago Okgetheng. I and Emanuela Budu will be presenting on word-based Bantu language identification using Naïve base theorem. Language is a very important aspect in communication, and we have language identification of text, and it has been one of the important aspects in natural language processing applications and pipelines. We have automatic language identification, which automates this process. This consists of applying computational methods to identify the language in a given text or in a given document. It is very difficult to discriminate language within language families than those across families. For example, we have Setswana and Sesotho, which is Bantu languages. They are coming from the same family. So it's very difficult to discriminate such languages. In addition, we have lack of training data. We have ambiguous language names, incomplete language code sets, and also incorrect use of language names in these two languages, which is the problems that we see in these two languages. There has been recent studies that have shown that language identification systems often fail to achieve satisfactory across different datasets and domains. With that, we have research objectives, which is to investigate word-based language identification using Naïve-based algorithm to automatically identify these two languages, which is Setswana and Sesotho. For the text of language identification, we utilize a multi-level Naïve-based classifier. In our methodology, the classifier identifies language by assuming that each feature in the text corpora is independent, and then it assigns a probability to indicate the language of the text. Next, these probabilities of all features are multi-level language, and the language with the highest probability is selected as the language of the given text. Given a set of language classes C and a corpus of size n, the classifier will assign the class with the highest probability to a given word I for that particular word using the Naïve base rule, as you can see the Naïve base theorem in there. And then we have our corpus. Our corpus is the one that has our text written in there. Our corpus is a different documents, and then we start with stripping this document. From there, we convert our document or our text to lower cases so that they can be in the same case. And then we do tokenization. In our tokenization, we are just splitting our text with a space as our language allows that. And then we assign labels to this each word, and then we do term frequency vector for each word. After that, we trained our model, and then we test our model, and then we evaluated our model. In our data set, we had a collection of words from various texts written in Sesotho and Setswana, and then we involve data pre-processing, which involves removing of stop words, punctuations, converting to the same case, which is a lowercase, and then doing tokenization, and then from there we obtain a time frequency vector. In our evaluation, we use precision and recall metrics, where we do precision with true positives and false positives, and the accuracy with true positive and true negatives, with that that formula where you divide with true positives and true negatives, and then we do our recall, and then we do our F1 score, which uses the precisions and recall metric. And then with our confusion metrics, we use 2.209 weights, where we have true negatives, which is 239, and then we had false positives, which were 37, and then we have false negatives, which were 121, true positives, which were 156. And then after that, from our results, we increase now in a way to try to see the variety when we have more weights, which we use 4.408 weights. And here we had true negatives 391, false positives 175, false negatives 71, true positives 468. And then with the summary of our results with 2.209 weights, the accuracy we got is 0.71, which is 71%, where the precision was 0.66 and the recall was 0.87, and the F score was 0.75 for Sesotho, and for Setswana is 0.81 and recall of 0.56, which gives us an F score of 0.66 in Setswana. And then with after increasing our weights to 4.418, we had an increase in accuracy from 0. To 0.78, and then here for Sesotho the precision was 0.85, the recall 0.68, which give F1 score of 0.76. And then for Setswana 0.73, recall of 0.87, which gives a F1 score of 0.79. From our findings, it reveals that the Naïve-based classifier can identify Setswana and Sesotho text as significantly a higher accuracy. However, we had shortcomings from the classifier, and it fails to classify homographs. Homographs are those which are very similar with different namings. And in future, we hope to address how homographs are perceived by the classifier to improve the performance of our classifier. This also in recommendation, we with this research, we can extend it in future to implement a syllable identification and sentence identification of word base to improve the accuracy of this classifier, because it was just based on the word, as because of previous research, people were using character by character to use this classifier. That's why for us, we want to see how would it perform when we use a word-based to identify these two languages, because they come from the same language, Bantu languages, which most of the words are the same. So which means that verb and noun morphology it's almost similar, which makes it in terms of writing systems to be more similar as well. That's why we identify the problem in there and try to improve it. That's the end of our presentation. We'll be waiting for questions. Thank you.
Thanks, Boago. I think that this work in this area is so important. So obviously, one of the potential weaknesses of doing what many people seem to have to do when you're generating these kind of corpora is to strip out words and then have individual words in each one labeled individually. And you've highlighted the issue of homographs, where you could have 2 or 3 words that are spelled the same but maybe pronounced differently and may have completely different meanings. And because there's no contextual language around them, it's maybe difficult to separate them. The other thing that's jumped out at me was that it seemed that you doubled the number of words in the corpus, but only increased the accuracy by 7%. Now, that's not a criticism, that's an observation. So the question I have in that regard is, at what level and with what likely size of corpus in terms of words would you consider an adequate accuracy rate could be achieved? And what do you believe an appropriate accuracy rate should be? Thank you.
Oh, okay. Thank you for the question. First, I will start with the one that was asked in the chat, which was asking about if
well, if you just answer the question that I've asked, and then I'll call on Kreol to ask the question themselves. Is that okay?
Oh, okay, no problem then.
I just didn't see him before I asked the question. Sorry.
Oh, all right. No, okay, let me answer your question, which was talking about the adequacy of our corpus that we use. With this corpus, we're trying to come up with a variety of words, like in terms of how they are written, because with these 2 languages, they are closely or tightly related in terms that most of the words, they are borrowed from each languages. So that's why with the data set that we came up with, even though it was less weight, but we're trying to come up with the one that has most of varieties, because we're using weights as our features in our classifier. I think with the accuracy that we got, we say that it was a better accuracy.
No, I appreciate that, but the question I was getting at was that you gave 2 examples, one 2,500 odd, the other almost 5,000, and the accuracy level, if I remember correctly, only went up about 7% with essentially double the words. So what I'm wondering is, at what percentage would you be satisfied? Is it over 80? Is it over 90? And what size of corpus do you think it would need to be to achieve that level of accuracy?
I think with this languages, it's a very difficult question to answer, because most of the words, they are from both languages. And with what we are focusing on, it was the word itself as a feature. So it will more depending on the type of the words that you will be introducing, because most of the words, they are overlapping. They are almost the same from both languages. And the one that were distinct, it was with the one which has a QA and HLE and HI. So which was the one that was trying to make it much way different. I think with the corpus wouldn't have much effect where in this scenario. Maybe trying to use different combining different methodologies, which is n-gram or graph based with this classifier. Maybe they can try to maybe increase our performance.
I understand, thank you. Kreol, do you want to ask your question?
Yes, thank you so much for the podium. This is a very interesting study, and I found myself quite intrigued as to what you were presenting. But it left me also wondering if other languages were considered, because from the presentation, I only saw Setswana and Sesotho, and there are other languages such as Zulu, Xhosa, as well as Ndebele, whereby some languages or some words within them might sound different or similar. So I just wanted to find out if you also considered other languages in South Africa, or it was only restricted to those two. Thanks.
Okay, thank you for that question. We considered only Setswana and Sesotho because we wanted the languages which were very much closer. And we saw that most of the time when from our studies, most people, they will include Setswana or sometimes they will include Sesotho when they were doing. And as we have indicated from the start of the presentation, we talked about these languages being in the same family. So for some other languages which have some distinct, it's always much way easier to identify such languages. That's why from even the related work, we had most of classifiers who were doing much way better, having higher accuracy when it was done in across different languages. But most of the time, they were not using Setswana and Sesotho at the same time. That's why we decided to take those two languages because we are more familiar with, and Setswana as a native speaker, it was easier for us to even understand the writing systems. Thank you.
Thank you very much for that question. Are there any other questions or comments before we move on? If not, thank you very much indeed, and I hope that work continues. So the last presentation of this session is by David, and it's a case study on data collection in Kreol Morisien, a low-resourced Kreol language.
Hello, everyone, and thanks for attending my talk today. So first of all, I would like to present myself. My name is David Bastien. I'm the technical director at Hydrus Lab, which is a privately owned startup company that focused on the development of artificial intelligence products tuned for the local market. And we also provide data science services to the local market. So one of the main things that we wanted to do under our company was to identify the different technologies that were missing in the AI sector in Mauritius. So basically the AI sector is nearly inexistent around here. And one of the products that we found that would be really useful to some companies around here was to develop a natural language processing pipeline or NLP framework for Mauritius. And one of the main issues here was to be able to develop an NLP that was able to work with Mauritian Creole and understand Mauritian Creole. So we did some kind of an audit to be able to identify what was missing. So this presentation mostly focuses on that. As compared to previous machine learning presentation that you might have attended, where we mostly focus on algorithms, how algorithms work, and the performance of algorithms. Here we are looking at another problem, another step that is sometimes omitted, which is how to collect the data and what are the main steps and the main issues that you can get when collecting the data. So to start, let's talk a little bit about Mauritius. So Mauritius is a small island of the whole coast of Africa. It is around 2,000 kilometers of the coast of Mozambique. It was first colonized by the French and the British, who brought workers from Africa and India to work in the sugarcane fields and develop the sugar industry around here. This mixture of culture might have resulted in the development of a new language or resulted in a new language called Mauritian Creole. This language, which is basically French-based, is a language that is spoken by more than 1.3 million people in Mauritius, and is the first language of many Mauritians. So if you come here, you hear people like talking in Mauritian Creole everywhere, at work, in supermarkets, in the bank. So that's like a big thing around here. So what's the difference between Mauritian Creole and any other language? like French or English. So one important phrase or sentence that you should learn here is, let's go to the beach today, because you might want to go to one of our nice beach. So how would you say that is allons à la plage aujourd'hui? And if you compare that to French, which would be allons à la plage aujourd'hui, you find that some words are kind of similar. For example, plage and plage are the same, plage can be translated to plage in Mauritian Creole, and aujourd'hui can be translated to aujourd'hui. So phonetically, they sound similar, but Creole has its own grammar and vocabulary. It has been standardized, like in recent years, I think it has been standardized, and we have our own Mauritian Creole dictionary. It's being taught in primary school and at tertiary level, and it's well established right now how we should write Mauritian Creole and how we should speak it. Mauritian Creole is not the only Creole language that exists. So we have other Creole languages. For example, in the Caribbean and in the Indian Ocean, they speak Mauritian Creole. Seychelles, Réunion Island, or two other countries in the Indian Ocean where Creole is spoken, they have their own way of speaking Creole. Same as Haiti, where they also speak some form of Haitian Creole, and other islands in Caribbean where they also speak Mauritian Creole. So it's got a larger international exposure that some people may think, but still it's a really small number of people that speak Creole as compared to English or French worldwide. Our aim here is to develop a natural language processing pipeline framework for Mauritian Creole. So in a short way of saying it, it's called an NLP. So NLP refers to giving computers the ability to understand text and spoken languages. This method is really mature for languages like English and French, but we still lag behind for minority languages like Creole and Creole in general. So our task is to find a way to develop those technologies for those languages. As we will see, it's a really small market, but we have to do it as small startups. One of the main technologies, one of the first technologies that we want to develop is a speech-to-text system. So this is currently under development in the company, and it is a speech-to-text system basically converts audio conversation to its corresponding text. One of the tools that we want to use, or one of the frameworks that we want to use, is deep speech. This is an end-to-end neural-based speech recognition system, and in our feasibility study, we found that it could be easily applied to other languages. Of course, if provided with the necessary amount of data, and this is around 5 million to 10 million words worth of data that we have to collect to be able to train those algorithms. The second tool is what is known as an information extractor. So it englobes different tools like name entity recognizers, sentiment analyzers, or text classifiers. So what it will do is it will be able to extract bits and pieces of information from the large unstructured set of text that we get from our speech-to-text synthesizer. So this would be able to, for example, help us to combine with the speech-to-text, be able to analyze traditional media like radio and TV streams in Mauritian Creole. So where are we right now when it comes to natural language processing for Creole languages? The only language that has some form of NLP tool is Haitian Creole. So they have a translator by Google. And when you look at other languages, other countries, Mauritian Creole, Réunion Creole, you will find that there's really few NLP tools right now. So the reason for that is clearly simple. If you look at the market, it's around 1.3 million, 1.2 million. It's a really small market, and it's not really the priority of huge tech giants like Google or Facebook. So in a sense, we have to get the job done ourselves, and startups like us is helping out in building those tools. And it has to be done. It's really difficult. So we are doing in some way the nasty job of getting the job done for those small markets. So yeah, tech giants, it won't really be a priority for them. So we have to do this. So how would we define a low resource language? So I can break it in 4 categories. We've got highly resourced, moderately resourced, under-resourced, and low-resourced language. So highly resourced languages are languages like English, Chinese, or German, or French, where they have huge data sets, use really good, well-performing algorithms. And on the other spectra, we've got no-resource languages. So no technology, no data sets. They are mostly minority languages or endangered languages. And in between them, we've got moderately and under-resourced languages. They can have some form of technology or small data sets. Mauritian Creole right now is like a no-resource language, between a no-resource and an under-resource language. So what we have to do is to get Mauritian Creole to be at least the moderately resource language, be able to have an MVP, and minimum viable product. So this is like a huge task that we are currently doing, and it's not impossible. It can be done if we get the necessary data. So our own whole data collection pipeline is broken down into 2 parts. You've got the data set creation and the model creation. The data set creation involves the 3 main steps. So the first step is the content is created by radio broadcasters, and we on our side will record those shows, those conversations through our radio recording station. Then we would send those data, those audio, to transcript and annotators. They would transcript the data and annotate them. So at the transcription stage, we would just type in what they hear in standardized Creole. Then they would annotate, identify brands, name, people names, do a sentiment analysis. Then the data should be curated. At the curation stage, the data is transformed into a form that can be input into the machine learning algorithm. Once this is done, we get into the model creation stage. At this stage, we would train the model and evaluate it. This is a feedback loop. So each time it is evaluated, we would have to communicate with the evaluator, would have to communicate with the language technologist, would tell them, okay, now I think we have to increase the accuracy. This is the accuracy. So they would fine-tune the algorithm up to a point where it cannot be fine-tuned with the amount of data that we have. At this stage, we would decide, do we have to collect more data? If yes, then we repeat the loop. So this would be like a never-ending loop until we get like an accuracy between 80% or 90%. So one thing that you should bear in mind is that the first cycle could take around 1 to 2 years. So that's a tedious task that has to be done. Right? So when it comes to speech to text, we've been able to transcript around 250,000 words. So that's around 5% of our objective. And one of the things that we have to look into is about micromanagement. So the way we're doing it right now is sending audio files, and people are doing the transcript and sending it back to us, and we are sending it to another team to do the annotation, and we are sending it back to us. So one thing that we should do is to have one whole system, a micromanagement system, where you can do the transcription, the annotation, do the task allocation, do the payments and everything. And there's an existing tool that can be used, and we are currently negotiating with this company, which is Datazo. So they have this system where you can just upload audio files and transcript them and just manage everything from one platform without bothering about anything else. And you can upload your models if you want to assist the transcript, or you can upload your dictionaries if you want in Mauritian Creole. Another thing would be to increase our team from 5 to 10. So with the micromanagement system, double our team to be able to get more than this 5%, maybe get to around 60 to 17% in like 6 months or 12 months. One thing that we found was about the data purity, which is affected by code switching. So code switching is basically when people are switching to French or English, and this might affect our data. For information extraction, we found that unsupervised machine learning can be used to analyze Kreol text. It's really useful. And one of the techniques that we used for feature extraction from text was force text. And we fed them into unsupervised machine learning algorithms like isomap, and they were able to easily identify patterns in text in Mauritian Creole. So this is a good sign that we can use machine learning and natural language processing, within natural language processing, and tools like force text and isomap to analyze text in any other language or low resource language like Mauritian Creole. So finally, what I can say is that we are like between 5 to 10 years late in terms of NLP training. So there's a lot of work to be done right now, and the technology might be here, but the data is not here, and we have to collect this data. One of the most tedious tasks was data collection and curation. This process can last between 6 to 12 months. Can't go around that, you have to collect the data. There's a lack of digitalized text. We don't have books, a lot of books that have been digitalized in Mauritian Creole. We have to collect the books and scan them to get enough data to be able to create models. Data augmentation can be a solution, but it is a plan B if it's not working. So we can do some kind of data augmentation or do transfer learning from French to Mauritian Creole to develop the algorithms. And yes, we have the technology. There's potential technologies that can be developed in Mauritian Creole for Mauritian Creole. And there's a market. There's a market of around 5 million people worldwide and 1.3 million in Mauritius. So there's some potential and some commercial potential. There's some research that have to be done. There's a lot of work. And yeah, so if we collect the adequate data, we can get the algorithm. So thank you, and I'm open to questions.
Thanks, David. It is particularly interesting to hear a presentation about essentially a no resource language. Most people talk about the second part of the pyramid, they don't go down further. So obviously targeting Kreol comes with special challenges. And yes, you mentioned that there is both a local and potentially a global market. But what are some of the specific challenges of creating what sounds like a unique corpus? So if I understood you correctly, if you're looking at a corpus of 5 to 10 million words, how do you do that? Is there enough literature? Is there enough technical manuals? Is there enough other content to make that possible? And then what are some of the similarities and differences with other versions of Kreol around the world? And how could you, or how do you intend to leverage these opportunities as a result? Thanks.
Thank you for your question. Can you hear me right? Yeah, so the first question is, do we have enough content? So the question is, the answer is simply no. We don't have enough text to, so for example, one thing that we could do would be to just tell people to read books, and we would just record that and see if we can record that and train the algorithm. So what we found out was that there were really few books in standardized Kreol. So the strategy was basically to record the radio. So that's like a never-ending source of information that can be used and data that can be used just to train the algorithms. So the question is simply, there's data, there's the content being created every day, but we have to collect it and build the algorithm. For the second question is, there's a slight difference between Mauritian Creole and other Kreol. So basically Kreol is between, I view it like being between two spectra, between English and French. So some languages, for example, such as Kreol, can be much closer to English as compared to Mauritian Creole, which is much closer to French. And Kreol from Réunion Island is much closer to French as compared to Mauritian Creole, which is like right in the middle. So one way is to do some kind of transfer learning between the different languages. So as it's much closer between each other, so it can be transferred from one language to another. But the other issue is for some cases, the grammar, the vocabulary is different. So the orders in which we might see the words might be different. So we have not yet explored the potential of using our model for other languages, but still we also have to collect those data. And this might be one of the big picture that we are aiming at, to collect data from the different countries speaking Creole.
Yeah, I think that might help you, but I think the idea of targeting radio in Creole makes a lot of sense. I mean, you're adding another layer of complexity, but still it gives you the content. Keneilwe, you had your hand up.
Yes, I did. Thank you so much again for the podium. You know, I'm finding myself quite interested in what has been presented today. I never thought I would be one to be interested in speeches and words and how that translate and how that can be compared. But I'm finding myself quite glued in what has been presented. If you look at the previous speaker, they were focusing more on South Africa and they just compared two languages. But what I liked about this was that it even went beyond just a single country. I mean, a single African country. It was in a context of others. And what I liked was at the first part, it looked at English speaking people, French, as well as Mauritians. And what I liked was the way, you know, it sounded quite, it's written differently, but sounded the same, even though it's written differently. And if you look at the context of just English by itself, and you just compare certain words, there are those certain words that sounds the same, such as your where with an H that would describe a location, in a way that would describe the past, something that has happened in the past. So what I have now is not really a comment, but to say that I'm really appreciative of what is being presented. It's more of a comment to say this is great work, and I'm quite interested in exploring this further. Thank you.
Yeah, it's really interesting to see how Mauritian Creole even goes beyond the African continent. So there's potential here, and these small companies, small research groups are doing the job. So that's what we are here for. Yes.
Yeah, and I think the other thing to keep in mind, Keneilwe, is that while we were just talking about two Bantu languages, there are more Bantu languages, and Bantu is Bantu languages are spoken everywhere from Central to Eastern to Southern Africa, you know, about 20 countries or more, and millions of people. So I think, to be fair, they were looking at a starting point. But I do think that the Creole offers a very interesting opportunity, because you're talking about different cultures both within Africa and around the world. And the very fact that there are variances, as David was explaining, between being closer to French or being closer to English or being in the middle or being at one extreme, I think there's a diversity and a complexity that is very rich. And I think if you look at the unfortunate situation where there are so many languages dying out, you know, where people are moving to urban centers, older people are not passing on the language skills because the younger people, you know, have other priorities, unfortunately. I think that Kreol is a very good example of how that kind of divergence of a common code, so to speak, is being used across the world. And maybe it'll offer some opportunities for at least trying to capture some of these dying languages. I know Kreol isn't a dying language, but it's in the same basket of many dying languages. So I'm hoping that some of the techniques that are being explained here today could be applied to help in that context. So David, do you have any final remarks before we close off this session?
So what I would say is, for languages, there's a lot of work to be done, and partnership with universities and other institutions is really important. So to be able to collect the data. So that's one thing. So we need to partner, startups have to partner with universities to be able to collect this data. And we should not just stay on our side and be doing our research on our own. So collaboration is really important with other African countries. So that's my final words on that.
Great, thank you very much. So I'd like to thank Misheck, Avashna, Boago and David for what I thought were very interesting and complementary presentations. We're going to continue next generation computing with a slight difference in focus after the break. So we're going to start up again in about 10 minutes. So enjoy your break, have a walk around, have a coffee, check your mail, and see you back in 10 minutes. Gurmila Market.